So this second talk today will be slightly different than the first one, and also slightly different than the other research talks that we had yesterday. Because instead of talking about what we do in science, I want to talk about how we do science, and in particular in how we treat and write the software that we use for our science. So this will be like an introductory lecture into software development, and I'll try to make it interesting.
Will you upload the slides?
I will upload the slides, definitely. And I would like to start by talking about the question why I should give this talk at all. And the first question that I would like to ask the audience is, how much lines of source code do you use for your research?
As few as possible.
As few as possible, exactly. Okay, it's an unfair question and it's also hard to answer. Let's make it easier. How much lines of source code did we use for the tutorials in the last 2 weeks?
1,000.
Any guess? 1,000?
1,000.
More?
Do we include that?
10,000? We include Aspect. We include every software package that we used. Aspect is not the biggest one. Surprise.
And like the Linux kernel?
No, we don't include the Linux kernel. We only include the the uppermost layer of software that we use.
100,000.
100,000. That's actually not too bad.
Does it include DL2?
It does not include DL2. It's about 500,000 lines. And most of them are actually in OpsPy. And I didn't expect that. Aspect has about 100,000. We didn't count DL2 with 700,000 lines plus 700,000 lines of tests. Vernon has about 25,000. Pythios 4,000 with a lot of documentation. So actually it's much more than 4,000. And all of the others, I wasn't able to count them, or I didn't want to bother counting. Okay.
How many lines did the code you write to count the lines have?
There are software projects for that. I didn't count those lines. Okay, the next question. How much did this cost? Too much. So there are many people in the audience who write proposals, and you know how to quantify the amount of costs for a day of ship time, or for a day of facility time, or something.
Berman was $10,000.
Vernon was $10,000?
And a lot of hidden costs.
Like
A lot of hidden costs, probably.
yeah, a lot of people working in that.
If you count all the people time.
Yeah, all the people time.
Yeah, exactly. So
Free time.
So there are estimates for this. And we can try to come up with one ourselves. So a skilled programmer in software development writes about 20,000 lines of code a year. And let's assume he has a salary of $80,000 just to make it simple. There are huge uncertainties.
That's what Berman is.
That's $4 per line of code.
Buys you a Starbucks coffee?
And actually, there's a huge uncertainty about this. So you can find interest everywhere from 15 cents to $12 per line of code, depending on the software. But let's assume our research software is relatively complicated, right? It's not just you want to write a user interface and you quickly write 1,000 lines of code. We need to do a lot of testing and benchmarking. So it's more on the upper end of the cost. So that means the software that we used for the tutorial is worth around $2 million. Which is comparable to quite a number of PhD projects or postdoc salary years. And also comparable to a lot of the lab equipment that we use. So I asked Rita what a typical mass spectrometer would cost. And she told me something like $500,000 to $1 million. I'm sure there are more expensive ones or cheaper ones depending on the quality. But the software that we use is actually worth as much as the equipment that we use. So how much time and money could we save if we could write this software in a better way? Yes?
The thing is flickering. I don't know if you can find
I'm not sure where the flickering comes from. I could try to
No, it's working.
try to change the projection method. Okay, so what's the current state of software development in science? A few years ago, there was this very amazing paper in PLOS Biology about best practices for scientific computing, and they summarized the current state of research, of software development and research. And I'm going to do the most boring thing you can do in a talk. I will read to you a few paragraphs from this paper. Make yourself comfortable, relax, and I'll let you know when I'm finished. So they write, software is as important to modern scientific research as telescopes and test tubes. From groups that work exclusively on computational problems to traditional laboratory and field scientists, more and more of the daily operations of science revolves around developing new algorithms, managing and analyzing the large amounts of data that are generated in single research projects, combining disparate data sets to assess synthetic problems, and other computational tasks. Scientists typically develop their own software for these purposes because doing so requires substantial domain-specific knowledge. As a result, recent studies have found that scientists typically spend 30% or more of their time developing software. Definitely depending on whatever you are doing. For me, it's more like 70%, but maybe for you it's more like 15%, but it's on the order of 30%. However, 90% or more of them are primarily self-taught and therefore lack exposure to basic software development practices such as writing maintainable code, using version control and issue trackers, code reviews, unit testing, and task automation. We believe that software is just another kind of experimental apparatus and should be built, checked, and used as carefully as any physical apparatus. However, while most scientists are careful to validate their laboratory and field equipment, most do not know how reliable their software is. This can lead to serious errors impacting the central conclusions of published research. Recent high-profile retractions, technical comments, and corrections because of errors in computational methods include papers in Science, PNAS, the Journal of Molecular Biology, Ecology Letters, the Journal of Mammalogy, and a lot of other biology journals. And I'm sure every one of us could add some papers from their discipline. No? So this looks pretty grim. There's not much training for software development in scientific curricula. And oftentimes it's just a programming course in a language. It doesn't tell you about how to develop a bigger software project. So in this paper, the authors make some suggestions about best practices for software development. Write programs for people, not computers. Let the computer do the work. Make incremental changes. Don't repeat yourself. Plan for mistakes. Optimize software only after it works. Document design and purpose, not mechanics. And collaborate. Now, maybe these researchers just had this funny idea about how software should be written and every scientist should spend this amount of time on these software development techniques instead of doing research. Oftentimes I hear the argument that you don't have the additional time to develop the software correctly because you also have to do research. So let's ask the people who actually make a living by writing software whether it's worth it to spend the time on these techniques. In commercial software development, there are many ways to assess the quality of a software and to talk about the best practices of developing the software. Many of them are extremely complicated, but there's one half-serious approach, which is called the Joel test, written by a blogger, Joel Spolsky, in his blog, that boils everything down to 12 questions. First of all, why should we care what some random blogger on the internet writes about how to write software? So for one, Joel Spolsky is a software developer that is in the business for 30 years, and he's the co-founder of Stack Overflow. If you ever had a question about how to do X in programming language Y, then you likely found the answer on this webpage. Secondly, and maybe even more importantly for us, he was the program manager for Microsoft Excel in the 1990s.
Oh, so we blame him.
Why is that important? He was responsible for including Visual Basic for applications and the macro language in Excel. And we used that language 2 weeks ago in Esteban's tutorial to compute the mantle potential temperature. So if he did a bad job 20 years ago by designing this language, we now compute the wrong mantle potential temperature, or would use a different tool then. Okay, so here are the 12 questions that he came up with. I'm not going to walk you through all of them, and clearly some of them are just designed for commercial software projects, so they are not of interest to us. Of the others, there are some that are particularly important that I want to talk about. Again, do you use version control? That was already in the first version of the best practices that I talked about. Do you have a spec or a documentation? That was also in the other one. Do you have tests? That was also in the first version of the best practices. And I just highlighted this because I found it interesting that one of the 12 most important points whether a software is written well is the working conditions for the programmers. Which is an interesting thought also for many universities who like to put their PhD students into big offices with a lot of noise. Let's move on. So, is the answer just using all of these commercial software development techniques that are out there? Probably not quite. Because the commercial software projects often are slightly different from the software that we write in science. There's this sketch about how scientific software development works. And that is, in the beginning, you really don't quite know what you want in terms of software, right? You have this vague idea, you need to analyze this data set, or you want to write something that models this or that. And then you start writing your software, and then you check, is this approximately what I want? And if not, then you make some modifications. And if it is, then you move on and you check it a bit, you see if the output looks reasonable, and then you say, okay, that will do. I'll stop here. That's quite different from what happens in commercial software development, because there often you have a contract about what the software actually has to do in the end. And you know from the beginning more or less what you want to have at the end. Also, as I mentioned, we have to balance the effort and the outcome of these software development techniques. Like, we have to do research, and we have to read papers, and we have to write proposals, and we have a lot of other things to do. So we cannot spend years learning all of these complicated software development techniques. We need to stick to the basics. Or we need to follow a different approach, and that was actually something that is currently under discussion and development in the UK. That's the career path of a research software engineer, similar to a lab technician. Like, at some point, the machines that you use just become too complicated that you can worry about every technical detail of the machine. But that's something that's not in the main scope of this talk. Also, the scientific software that we write is actually never really finished. So oftentimes, the development process of scientific software looks more like this infinite loop of designing, developing, refining, publishing a paper, and then start over again with an improvement software, right? So a third way to think about what the best practices of software development would be to go to your favorite trusted institution and ask them for best practices. And that's where the computational infrastructure for geodynamics comes in. Of course, you can use whatever institution you trust most. There's, for example, the Software Sustainability Institute in the UK, which also has a big list of best practices. But here I've taken the minimum best practices as they are posted on the website of CIG. And these are the 6 points that all software projects by CIG have to fulfill, at least. And again, you see that there are 3 points that already came up in the best practices of the 2 other sources: version control, testing, and documentation. And that's what I want to spend the rest of this talk on. Because these 3 techniques are the ones that you can actually do in your research that help you and that provenly save you time. Okay, so let's talk about version control. Why should you use version control? Maybe you have seen this PhD comic before. It's a story told in file names, and it's meant to be read from the top to the bottom. I'm sure every one of us has a similar set of data directories somewhere that are listed like this. Maybe without a few here, but anyway.
Huge changes in the size.
Yeah.
Yes. Consider particularly the Okay, how does version control help us avoid this situation? So for one, version control allows you to archive the history of your project. You can save every single snapshot, and you can always return to this snapshot later on, so you don't longer need to keep all of these copies around. So for example, you can answer the question, hey, what was the state of your project during last AGU when you talked to me about it? It also archives the decisions that you make, because every time you make a new commit or you save a new snapshot, you put a message there and shortly explain why you changed this. It also tells you what other files were affected by this change, so it archives the connections. And you can safely test inside of the same directory without having to be afraid of breaking something. You don't any longer need to make backup copies of this just in case you break something and can't go back. But there's something else, and that is if you do version control not only locally on your machine, but you upload it to some hosting host like GitHub or Bitbucket, then this allows you also to communicate efficiently with other people working on the same project. Maybe in your research group, maybe even bigger between research groups. And you can make developments in parallel, which only becomes important if you work on a bigger project, but still it's a nice feature. So what would the minimum workflow look like if you would want to do this for your next, say, CIDER project? Using Git, you can always start a new repository in any folder by just doing git init . After adding any new feature, you can add a file that you created or that you changed, and then save the snapshot of the current state with the command git commit -m, and you put in a message about what you changed. You can always check the history of all of the snapshots that you created and see when you did them and what the message was at the time. You will repeat this every time you make changes. And when you want to see past changes, you can use these commands, git diff, to see what has changed since then. There's an excellent Git tutorial made by an institution called the Software Carpentry, but it takes about 90 minutes to 3 hours, so there was no time to put it into this talk. But if there are people in the audience who are interested, I'm happy to walk you through this tutorial anytime later during CIDER. So you can have a talk about that later. Okay, let's move on. Tests. What do tests do? They give you the ability to trust your software. Because without tests, you shouldn't trust your software. I know how I write code, and I'm sure you know how you write code and how much you trust or not trust something if you try it the first time. If you have a test case where you know what you expect and you can check that your code exactly reproduces this, then this produces trust in your software. It also is much cheaper to fix these bugs immediately afterwards. There are estimates in software development industries that says it's about 10 to 20 times cheaper to fix a bug right away instead of fixing it a week later, because you have forgotten what you have done in a week. It also lowers the barriers for big changes. If you have a set of 614 tests, like Aspect, then you can rip apart your source code, you plug it back together in a different way, you run all of these tests, and if all of them pass, then at least you have a pretty good sense that you didn't broke any major functionality. Maybe something small that you didn't test, but at least everything, the big things work. And of course, it saves you a lot of embarrassment during review by your supervisor or by the review of your paper or somebody else if you already tested this functionality beforehand and found the bug before somebody else found the bug. So how would you do that? It's actually not that simple to come up with good test cases. But oftentimes, you can just imagine some very simple case and you know what output your software should generate for this case. So in geodynamic modeling, for example, we can often come up with analytical solutions for very simple test cases. Or in data processing, you could put in a totally artificial input signal where you know how the output signal should look like. If you are not able to come up with such a test for your feature, then at least run your code at the current time and store the result of your code at the current time. Because then you can repeat this process in the future and see if something changed. And if nothing changed, then at least you are at the same state as at the moment. Keep this test case and the data in your repository, because if you move it in some other directory, you will just forget about it and you will never run it again. But if you keep it in the same directory and you make it easy to run and you repeat it every time you make changes, then you're pretty sure that you didn't break something. Over time, you can accumulate many of these test cases and especially write a function that just executes all of them all of the time, so that makes it easier to run. And there are actually automated testing frameworks for nearly every programming language, but depending on the size of your script and the complexity of your software project, you might not even need that. Okay, documentation. Documentation is actually more complex than it seems at the beginning, because if you think about documentation, you likely just think about, oh, I should write there something about what I'm doing here in the code. But you can write documentation in a useful way, and you can write documentation in a not useful way. So let's consider this example out of the aspect source code. So something is happening down here. We compute some new stress based on some old stress and another new stress. So if the person who wrote this code would have written something like compute the new stress as a weighted average of the old stress and the new stress, that wouldn't help you much. This comment wouldn't help you in any way, because you can read this code and you see what is happening. You need to know why this is happening. And that's why the comment above says stress averaging scheme to account for difference between fixed elastic time step and numerical time step. See equation 32 in Morrissey et al. 2003. So this helps you if you want to know more about why we do this. Of course, I picked the best possible example of source code here, right? We also have useless comments. Okay, what does it do? If you write documentation in a good way, it preserves your knowledge. You know most about this part of the code right at the time when you write it. In a week you have forgotten about it, or at least in 6 months you have forgotten about it. It documents progress. It allows others to benefit from your work. They don't have to repeat the thought process, how you got here, if you have a good comment above it. And you give yourself a laugh here. Like, I don't know how often I hated myself for not documenting this line of code or this script, and how often I had to repeat all of the steps of thought process to know why I got here. Okay, so how to do it? There are some good points that I already talked about, and that is you should always document the intention and the motivation of the code here, and not the mechanics. You can usually figure out what is exactly happening mechanically by just looking at the code. You need to know about the intention behind this. You should always embed the documentation for the software in that software, and you should always write it while you write the software. Never write the documentation afterwards, because you just won't do it. Be honest to yourself. Like if you write 1,000 lines of code, you don't write 1,000 lines of documentation afterwards to document all of that. It's just not happening. And also, if somebody asks you about a certain piece of code, then oftentimes the first idea is, okay, I have to write a comment to this code to explain it. But oftentimes the fact that somebody asks you about this code means the code is written in a way that it is not understandable. And many times it's actually easy to rewrite this code in an easier way, and then you don't have to write the comment, which is the preferable solution. Okay, I'm nearly out of time. So what's the conclusions of all of this? Software nowadays is exactly as valuable as all of the experimental apparatus that we used for doing science. And it's also as complex as any of these machines. It's often not as probably attributed and supported and maintained because there's a lot of there's a big discussion about how to attribute software and how to cite software and how to recognize the creation process of software. And this is a great website to read more about this problem. But if you start your next research project, the minimum best practices that you can use and that don't take a lot of effort and that will save you time during the project are use some kind of version control, develop and maintain tests for the scripts that you write, and write the documentation while you write the code. As I mentioned, I'm happy to give a GitHub tutorial or a Git tutorial later this week to cover the first point here. And if you want to read anything more, there's a lot of literature and links on this slide. Thank you.
I'll just make a comment that I am interested in that tutorial, so to get the ball rolling, maybe other people can say yes.
Sure. I don't know, do we want to make a big raise of the hand if you're interested, or? Okay. Okay. Yeah. Okay, we'll have that tutorial later this week. I guess we'll try to find a room and a time and then set it. Yeah. Set it.
How long does it take to run the tests for Aspect?
So. All in all, 20 minutes. 5 minutes for compiling, 15 minutes for running all of the tests. And we do that every time before we merge any change to the code. So every change to the code has to pass all 600-something tests before it is merged. Yes.
So just a comment. So I just went through my first pull request. GitHub. And I was really fascinated when they were like, you have to make a test because you made changes. I was like, all right, how am I going to come up with a test? But there's a whole library of tests already there. And it was amazing how simple the test needs to be because you really want to just test just that one thing that you changed. And so once I understood the concept behind the test, it was really easy to come up with a test for every change I want to make.
Yeah, exactly.
So, yeah. There's so many examples to work from.
So these tests don't have to be full benchmark studies. Like they are really just designed to test. The smaller the feature that you want to test, the easier it is to come up with the test. And you want to have as small tests as possible because when one of them breaks, you can immediately see which particular feature was broken. You know exactly to which line of source code you have to go to fix it again.
So, in your opinion, is it better to put everything in one giant code or to have many functions and maybe even functions within functions?
So there is some philosophical argument about the correct size of a function in computer science. My advice would be try to make it fit on 1 or 2 screens in length. And if it's longer, then write a new function. There are people who argue for functions that have at most like 5 lines of code, and others who argue for functions that can have a few hundred lines of code. Somewhere in between there's a sweet spot. If I can make one more point that I see again and again. Our screens now can fit more than 80 characters in length. So there's absolutely no point in abbreviating variable names anymore. No point. For anything, like there is no point in naming a variable. Sorry to pick out sitcom, but it's an example that I just have in my head. There are variables that are called SX.
Yes. I don't know that.
Yeah, exactly. Me neither. If I remember correctly, it stores the coordinates in spherical coordinate system for every vertex of the mesh. it took me a while to figure out that that was the meaning of SX.
Screen was smaller.
Yeah, definitely. No, I'm not arguing that it should have been done differently in the past, but like now we have like full HD screens or 4K screens or whatever. It's much easier to read if it's human. So that is actually this first best practice of the paper in the beginning. Write programs for humans, not computers. For computers, it doesn't matter how long this variable name is, but it matters for humans who have to read your code. And code is usually, you read code much more often than you write it. And you have to understand it much more often than you write it. So it's easier to make it more expressive and easier to read.
But for the GitHub thing, do you use it on your like personal computer, or you can install it on a supercomputer?
So GitHub is a web page that uses the Git version control system. So GitHub is only the hosted part from a company, well, by now from Microsoft, but
copy the source code from supercomputer to your whatever to the.
No, they use the Git version control system, and the Git version control system works on Linux, on Mac, on Windows, I think as well right now. Definitely using the Linux subsystem for Windows.
You just need internet.
Exactly. So the only thing you need to use Git and to upload things to GitHub and download it again to your computer is internet.
But it can be local, can't it?
Git alone can be completely local.
Yeah.
And that's what I showed on the slide about what the simplest steps to use version control. Where's it? Here. So all of these commands will only keep the history of your project local inside of the folder that you have. And you don't need to have an account, and you don't need to worry about any data security or anything. It's just in your directory. Okay.
Just a quick question. I was curious what your thought is on open versus closed source on scientific code. And I'm not even talking about like the really big codes, even just like smaller codes, but are used for like a single or multiple publications.
Yeah. So in general, I would advocate for open source software. That's also CIG's position on science software, because it's the concept is similar to open access in a way, that if you write something and you want to have it published, open source has a lot of benefits to it. Like you can get attribution for this software, and other people can use it and can avoid duplicating effort and all kinds of things. Now, if this is important for your one visualization script that you might write for a paper, that's a different question. There's likely no point in trying to promote this script. There's certainly a point in making this available, because if people want to reproduce the results in your paper, it's a good thing to include that in either in the supplementary information or upload it as a project to GitHub. But you don't need to apply the same strict standards for open source for these smaller things.
Just the last question. See the aspect logo on your shirt. Why your program is so much harder than learning?
Because this is an incompressible simulation, and we started with a linear temperature profile, so initially you just get a big overturn.
So there's a physical reason.
There's a physical reason behind it, and this physical reason is actually the reason why we are looking for a new logo since a year or two, but we have not managed to come up with one, so we just keep using it. Okay.